Welcome to the IDSS-Targeted Threat Messaging course. This is the second course unit that focuses on what TTM is. I'm Pete Wolf, the SUE at the Weather Forecast Office at Jacksonville, Florida. The concept of TTM really focuses on communicating hazards. When I was a forecaster a very long time ago, no one really ever told me about the importance of not just what you message, but how you message. Somehow I just knew it, which led to a lot of job satisfaction during many events in my career. I will also say that back then, we had to manually type watch and warning products, but that gave us full control of the message, allowing us to communicate better information compared to the more automated approach today. One of the things I hope you'll learn is that TTM is not just valuable to partners we serve, but also valuable to forecasters with regard to enhancing job satisfaction. I want to tell you about two events I personally worked that really highlighted for me the value of TTM. The first was an EF3 tornado in the southeast corner of Georgia, a short distance north of the Jacksonville Forecast Office, a very rare event for southeast Georgia. It came from a large supercell with clear signatures in a favorable environment, supporting long warning lead times. Warnings met our mission, but alone limited our messaging ability. What we did differently in this event, however, was use NWS chat to message every 5 minutes the precise location and motion of the likely tornado, given we could see it on velocity imagery, and also indicate the next town or highway in its path. To our amazement, within 30 seconds of each chat message transmission, we heard it read word for word live on local TV stations. In other words, we had complete control of the message. We held the microphone in front of potentially a few 100,000 people within a 1.5 million person viewing area. Incredibly satisfying, given that a significant tornado indeed occurred, as shown here. Now, it's not terribly difficult to track and message an obviously severe and potentially tornadic storm. It's more challenging to accurately message what hasn't developed yet. Consider an event that occurred 10 years earlier in southern Georgia. On a typical warm season day shift, with our usual small chance of afternoon thunderstorms like we have every day then, I received a call from the emergency manager in Wayne County, Georgia, asking about the potential for heavy rainfall. You see, in that area, they have a lot of dirt roads, which in heavy rain become mud roads. Not good for school buses, or any other vehicles for that matter. So their school board was assessing if school needed to be concluded early to get students home safely. The radar didn't show much, nor did our model guidance, so I briefed him on the potential for isolated afternoon storms, but likely nothing too substantial. Oh, was I going to regret that one? Shortly after the call, the forecaster I was working with came up to me and pointed to a few narrow bands of very light showers on radar. What was odd was that these bands were moving toward each other, likely representing boundaries that were going to collide in about 90 minutes, right over, you guessed it, Wayne County, Georgia. My heart sank. So after the cursing ended, I called the emergency manager back and indicated that while radar still didn't show much, it did suggest weak boundaries that are likely to collide over central Wayne County in about 90 minutes, which could force the development of a band of thunderstorms, given the unstable environment in place, with the thunderstorms going nowhere, given the lack of any flow aloft, resulting in flood-producing rain. Well, about 90 minutes later, the boundaries collided. Storms erupted over central Wayne County and moved very little. I believe a flood warning was probably issued for that event. When it comes to simply messaging what is occurring now and what you're tracking, the task of TTM is fairly simple. But near-term forecasting of hazard development and impact is considerably more challenging and requires effort. It requires good science and good data, but it can be incredibly rewarding from a satisfaction perspective. My second briefing was far more satisfaction than my first one. This module will describe the value of TTM to partners as well as the meteorologist through the watch and warning periods. It will review a few exercises to illustrate this value compared to what is provided in watch and warning text products or graphics. IDSS is about providing information, not just weather-related, but impact-related as well, to support the decisions people make. Isn't that really what operational meteorology is about? TTM is downscaled messaging that supports specific decisions or sets of decisions to be made by those we serve. decisions that may not be sufficiently supported by information that is not downscaled. So essentially with TTM, we're utilizing science and technology to add a level of preciseness or specificity to support actionable decisions through a range of lead times. So how does TTM, an aspect of IDSS, relate to the Weather Service warning program and our mission? As you know, our mission is focused on protecting life and property. Warnings are the flagship product, the only real requirement for WFO operations. But are warnings the only thing we need to meet this mission? Do they provide the detail needed? When it comes to warning response, there are steps that people take. They confirm the threat is real. They personalize it, that the threat exists for their specific location, and then assess action. Do warning text products provide the information and the scale to allow one to achieve these steps? If not, what could we utilize to augment warnings to achieve this? This is where TTM fits in. Our future is focused on IDSS, with greater focus on impact than simply weather conditions. Our greater focus is also on supporting the diverse decisions that a variety of people and partners make. This includes more than the decisions just to take immediate protective action. I do want to point out that TTM is not a new thing in the Weather Service. I've been involved in it in some way over my entire 30-year career. Back before the modernization, forecasters had to manually type and broadcast warnings and statements. On the positive side, it gave us control of the message. We could type what we wanted to communicate. On the negative side, there were typos, and it took additional time to create and issue the products. Then came the modernization, and with it a shift to automation. We had WarnGen, automated voice for weather radio. This led to faster issuance and broadcast and got rid of typos. But on the negative side, it took away messaging control from the meteorologist. Then came the internet era and social media and so forth, and with it, opportunity to regain messaging control. TTM is also an important item for TV meteorologists. Consider what happens when you issue a tornado warning and the TV meteorologist is broadcasting live, starting with your 300 square mile polygon, and then downscaling it to the hazard signature and the towns immediately in its path, which may not be mentioned in the text product. Possibly downscaling to a 10 to 20 square mile area, downscaled messaging. When I refer to the power of TTM, I'm really referring to the phrase control of the message. Because you see, the human still outperforms current technology when it comes to downscaling threat messaging in time and space to support actionable decisions. TTM gives the meteorologist the ability to control the message more accurately and precisely than what comes out of WarnGen or hazard services. We can provide information that supports threat confirmation and threat personalization that hopefully yields correct response. And through it, we can achieve a higher level of personal satisfaction from high-impact operations by exceeding mission requirements. How would you answer this question? True or false? Science and communication have equal roles in the success of TTM. Hopefully you answer that true, as TTM requires both science and communication. That's and, not or, not one or the other. Consider a situation where the TV meteorologist is focused on what appears to be a tornado velocity signature, but in fact it's bad data due to sideload contamination. The wrong information gets communicated. We need good science and accurate communication. The science part involves not just radar analysis, but also knowledge of storm environment. The communication part means offering the science in English, with focus on what, where, and when, and not so much on the how or why. For TTM, we'll focus on two general periods. The first one I'll call the pre-impact period, and this covers a few hours before impacts, so mainly in the watch period, except warnings for winter storms. The second is the impact period itself, which we're mainly talking about during warning periods. What about the outlook period, which can be 12 or more hours ahead of the event? Well, much greater uncertainty can exist, making downscaled messaging more difficult. Consider severe storm outlooks, for example. SPC has good skill in forecasting where severe storms will occur, but the skill level for accurate coverage forecasting is considerably less. What our guidance suggests will occur 8 to 12 hours in advance can change as the environment changes, leading to a different result, which may not become obvious until perhaps an hour or two ahead of the event. Here are some examples. In each one, an X marks an area over forecast where very little occurs, while an oval highlights an area where greater coverage occurs than forecast. What occurs might be more predictable just before the event starts than 6 or more hours in advance. Thus, we might be able to communicate more confidence in expectations 1 to 2 hours in advance compared to 6 to 12 hours ahead. Forecasting small-scale flood-producing rain events in advance can be equally challenging. Here are some examples, with small-scale events occurring within large marginal risk areas. The red ovals highlight the actual events. Knowing exactly the area that will receive excessive rainfall may not become apparent until shortly before the event begins. So our TTM focus will be from shortly before hazard development through the hazard existence period. An hour or two before severe storm initiation, we might have large-scale watches in effect for a 6-hour period, referring to potential across that area during that lengthy period. But we have tools and technologies that can allow us to downscale that message to support information on where severe storm initiation is most likely to occur during the next 1 to 2 hours, and the ability to communicate that information to decision makers. In this example, we have a band of enhanced cumulus along a boundary in southeastern Oklahoma where the cap is becoming weak enough to support storm initiation. And thus we can focus messaging on that, as it's not in the watch product. Later, as storms initiate along the boundary, in a favorable environment for severe storms, we can focus messaging on areas to monitor for potential warnings. Here's an excessive rainfall example. We have a large flood watch area covering a large portion of 2 WFO areas of responsibility. Excessive rain occurs over much of the watch area. Let's focus on downscale messaging for this small part of the watch area, north and northeast of Wichita, Kansas, that received 5 to 10 inches of rain. I won't go into detail, but the environment favored backbuilding and training convection. The question was where exactly that would set up. Radar imagery at 19 and 20Z show the development of a band of convection north of Wichita, with storm motion being eastward. As cells due north of Wichita shift eastward, new storms form upstream. This might be the time to message flood potentials north and northeast of Wichita, well before radar rainfall estimates total enough for a flood warning. In other words, provide longer lead time before flooding occurs. Look how the band sets up, east to west, with new storm initiation north and even northwest of Wichita. This is a dangerous pattern. Over several hours, 5 to 10 inches of rain fell north and northeast of Wichita, approaching double flash flood guidance. TTM can be a tool to provide lead time messaging of potential before the flooding initiates. We can do the same thing for winter storm hazards. Let's focus on an event from February 2022 for the Kansas City metro area, where 8 to 11 inches of snow fell. Here is the winter storm warning product, focused on 4 to 6 inch snowfall with gusty winds that will produce dangerous travel conditions. Note that the warning text product provides general threat information for the entire warning area. So significant impacts are indicated during the period from midnight Wednesday night all the way through the day Thursday. Let's start at midnight, just before the event, when the warning product was suggesting the starting period of potential impacts. So at midnight, radar was showing rapid development of precipitation across central Kansas. Model guidance spreads this precipitation across the Kansas City metro area after about 4 a.m., with impacts continuing through the morning rush hour. Currently, it's above freezing in Kansas City, but cold air advection is expected to lower those temperatures to the upper 20s just before dawn. The precipitation across central Kansas is in the form of rain and sleet, but with colder air spreading southward, the precipitation will become a wintry mix later at night, likely changing to all snow by dawn. So, look at this question. We have a warning for the area covering the next 18 hours. How might we downscale a message for the Kansas City metro area regarding any impacts over the next 2 to 3 hours? Will it be bad, or will conditions be fine? Actually, we're expecting minimal impacts through 3 a.m. with the precipitation well to the west and southwest of Kansas City. So conditions should be fine. This is not indicated in the warning product, but we can indicate it in short-term messaging. By 3 a.m. local time, precipitation is spreading closer to Kansas City, We have a wintry mix spreading in, with surface temperatures now down in the upper 20s, but sleet and snow are dominating across the western portions of the precipitation area, with some quite heavy. So in this question, how might you downscale a message for expected impacts for the Kansas City metro area through the morning rush, say through 14Z? Well, we have precipitation moving in, so we would expect steadily worsening travel conditions through the morning rush as bands of heavy snow and sleet spread across the Kansas City area during the rush hour period. Through TTM, we can provide more detail and specificity, not just about weather conditions, but also resulting impacts. At 12Z, we have heavy snow spreading across the Kansas City area. The back edge of the heavier precipitation is gradually shifting eastward, but the model suggests that with the upper system starting to lift more northeast, that band of heavy snow may remain over the Kansas City area until around 18Z. How might you message expected impacts for the Kansas City metro area through the morning? Obviously, we would expect dangerous travel conditions through the morning with rapid snow accumulation, making it hard to clear roads, and that travel should be avoided. So even for winter storms, we can provide TTM focused on near-term impacts. Let's turn to short-fuse convective warnings. Here's an example focused on an eastward-moving tornadic supercell. The text product is on the left and the polygon on the right. Given a steady eastward motion of this storm, deviating from an earlier east-northeast motion relating to the cloud layer mean wind, what towns shown within the polygon do not appear to be in danger, despite being mentioned in the location impacted section of the text product? The answer is highlighted here, including towns not just well south of the mesocyclone tract, but also ones behind the mesocyclone. This results when a polygon is a bit too large relative to the actual area of threat. Where might you actually downscale a message that focuses on the towns that are in immediate danger, where quick protective action is needed? The blue oval focuses on the area immediately downstream of the mesocyclone, covering towns like Russellville, Dardenville, and Pottsville. Can the human communicate who is really in danger better than what automation provides? Here's an example from the December 10th, 2021 tornado outbreak. We see a pretty large polygon surrounding a smaller hazard. For a northeastward storm motion given by the white arrow, for what towns would you focus a downscaled message on the immediate tornado threat within the larger tornado warning area? I'd be focusing my message on the blue polygon area, immediately in the path of the mesocyclone. So that would include Hornersville and perhaps Rives. 10 minutes later, the mesocyclone is passing over Hornersville, at which point we could start messaging the next downstream area, including Rives, Gobbler, and Deering. If the favorable environment extends well downstream of the polygon, our messaging could focus downstream to support longer lead time decisions. Let's focus on an hour in advance. What towns could you mention potential for a tornado, and thus the need to pay close attention to the approaching storm by that time? Note that the white arrow represents a 15-minute motion for the mesocyclone. Assuming a favorable downstream environment, giving me confidence that this long-track tornadic supercell will continue downstream, I would focus that messaging on towns like Tiptonville, Windberg, and Ridgely. In this example, Tiptonville was struck by a strong tornado from this storm. So now let's try a few severe storm event case exercises to demonstrate the value of TTM in high-impact severe weather operations. Let's start with a fascinating event that occurred on June 11th, 2022, and our focus area is the WFO Topeka forecast area of northeastern Kansas. You see here the Storm Prediction Center had a slight risk to enhanced risk, particularly over the Kansas City forecast area and extending into southwest Iowa. Our area of interest had a slight risk in the eastern portion and a marginal risk on the western portion. Here are multiple runs of the HRRR showing forecast updraft helicity tracks. This looks interesting for that enhanced risk area. However, do you see a trend with time more westward focused? And even with tracks that are oriented a little more north to south oriented, especially on the western side with time here. Here was a graphic from the local office focusing on the slight and enhanced risk areas, indicating a potential for severe weather and the time frame. I was the arrow showing a southeastward direction of motion. So looking at some of the SPC mesoanalysis page data, we see Generally a very unstable but capped environment over Kansas and Nebraska. But over time, by 20Z, we see an erosion of that cap over east central and southeastern Nebraska, in about the area where we also see converging surface winds. And we can see that increasing surface moisture convergence across southeastern Nebraska, whereas across the enhanced risk area around the Kansas City forecast area, we actually see diverging surface winds. And we can see that again here on the 20Z surface map. We can see the winds pointing into southeastern Nebraska, substantial mass convergence there, whereas across northwestern Missouri and northeastern Kansas, we have diverging surface winds. And we also see that on visible satellite imagery. We see building cumulus where we have mass convergence across southeastern Nebraska, and even ahead of a cold front moving across northeast Nebraska, whereas we don't see a cloud in the sky where we have divergent flow in western Missouri and far eastern Kansas. So my area of focus, just from what I've shown, would be where we have that area of convergence and weakening cap, as highlighted here. The latest run of the HRRR at 21Z now focuses almost entirely on a significant UH track that dives southward across east central Kansas. It shows much less over northwest Missouri and actually forecasts that much later at night. So our main focus from the HRRR through the afternoon and evening is this one big track. We see that on composite reflectivity with a storm that shows over southeastern Nebraska that actually is not too far off from what radar was showing at 21Z. And you see that storm is forecast to dive southward into east central Kansas over time. Not a whole lot further east in Missouri, at least through 1Z. This is pretty much backed up as well by the 18Z high-res NAM model, showing a little greater coverage of storms over southeast Nebraska, but once again diving it southward over east central Kansas with not a whole lot in the enhanced risk area. At this time, the Storm Prediction Center issued a severe thunderstorm watch that covers northeastern Kansas, as shown here. And from that, the local office graphic is updated to focus on the watch area. Notice also the direction of motion is indicated to be a little more southward now. So if we were to try to downscale a message of where we think severe weather is most likely during the next 2 or 3 hours, where would we focus on? Would we focus on the slight and enhanced risk areas off to the east? Or would we focus on an area further to the west, given the latest trends? Given storms developing and moving almost due southward towards Kansas, the Storm Prediction Center is focusing further west, the western part of the watch area, in fact, where we might see significant severe weather. And that's, in fact, what happened. The main event actually came down the western side of the slight risk area, across east central Kansas. Not a whole lot ended up occurring in the enhanced risk area. On the warning side, here we see a storm cluster that's turning due southward into far northeastern Kansas. How might we message the threat? And for which time periods could we message it? Would we focus just on the imminent threat area during the next 15 minutes? Could we message areas that have a 30 to 45 minute lead time? Could we message further downstream if the environment is favorable, an hour or more downstream, to what to pay attention for? Could it be, in fact, all of the above? Let's look at a second exercise. This time we're looking at March 31st of 2020 in southeast Georgia and northeast Florida. This is another interesting thunderstorm event. As you see, we have a slight risk across southern Georgia and a marginal risk along the I-10 corridor in far northern Florida. Later in the day, we see a small area of enhanced risk being posted for the Florida Panhandle into southwest Georgia. So at 1730Z, we'll start with this radar mosaic showing thunderstorms moving into southwestern Georgia and moving across the Florida Panhandle. We see weaker activity as you go further to the northeast. The NAM and the HRRR show fairly similar solutions, with a band of intense storms moving across southern Georgia, thus the need for the slight risk across southern Georgia, right? At 850 millibars, we have a low-level jet across the Florida Panhandle into southwestern and central Georgia, which is expected to veer and spread eastward across northern Florida by 0Z. And we can see a reflection of that in surface winds, with gusty surface winds across the Florida Panhandle and into northwestern Florida, a little more stable as you go further north, and the winds aren't quite as gusty up there in central Georgia. By 18Z, we see destabilization across northwestern Florida with temperatures in the 80s, dew points climbing into above 70, still stable, and actually you see a lot of rain icons across southwestern and central Georgia. And then by 20Z, we see stable conditions, temperatures in the 60s across southern Georgia, and near 80 or even low to mid 80s in northern Florida. As we look at this from a satellite perspective, between 17 and 19Z, we see a northeast to southwest oriented band of convection, parallel to that 850 millibar flow. In such a pattern, we tend to see the more intense convection develop on the southern part of the convective system, with a broader area of stratiform rain expanding to the northeast. And we see that in this animation through 20Z. The most intense convection evolves more southward toward the eastern Florida panhandle, with just broad rain with embedded convection across central and southern Georgia. Things are changing environment-wise. We have a tornado watch that's in effect from southern South Carolina all the way down to the eastern Florida panhandle, covering the potential for damaging winds and isolated tornadoes. However, within this large watch area, do you think there's an area that you might try and downscale where the threat of severe weather is much greater than other areas of the watch? What area would you highlight with greatest potential of severe weather, mainly wind and tornado, during the 2-hour period from 20 to 22Z? I would focus on the southern part of the line, across far southern Georgia and mainly across northwestern and far northern Florida during this period. By 22Z, we see the line of storms moving across northern Florida, much weaker activity as you get much further north and northeast of Florida. We have a strong low-level jet oriented west to east blowing across this line, supporting damaging wind potential and even the potential for isolated mesovortices along this line. So my threat area now focuses just on this area of northeast Florida. We have the entire watch in effect, but this is the area of focus for me, not across southeastern Georgia at this point. And here's what actually happened. We've had a change in the environment due to how this convective system developed, with more intense convection further south and more stratiform rain with embedded convection across central eastern Georgia. As a result, we had very little severe weather across southeastern Georgia. And the activity actually ended up in the marginal risk area along the I-10 corridor of northern Florida with tornadoes and damaging winds. Much of that damage was due to this mesovortex that you can see here on radar moving across northern Clay County and into far southeastern Duval County. Tornadoes and damaging winds resulted. Not much else occurred elsewhere along the line. Hopefully you can see in those cases the benefit of downscaled messaging to augment what we can provide in watch and warning products. As you may have noticed, I have not provided detail on the how, right? How do we message downscaled threat information? This will be the focus of the next part, Unit 3. So TTM focuses on control of the message, providing a greater level of detail than the more generic watch and warning text products provide. The human is better at providing this detail in an accurate and timely manner than tools like WarnGen or Hazard Services. TTM is challenging to provide during the outlook period due to much greater uncertainty, but it can become valuable as one gets within a few hours of potential impacts. TTM supports downscaled messaging with more impact-related detail needed to support threat confirmation and threat personalization, the key steps that yield timely, actionable decisions to warnings. Thank you for completing this module. Hopefully it has effectively demonstrated the value of TTM for effective IDSS and our ability to provide it. An important aspect of this is effective communication of threat information, which will be the focus of Unit 3.